homeostasis the functional design of living things? Living things, whether they're unicellular or multicellular, function to maintain homeostasis. Now, if you take the word homeostasis apart, homeo is the same. Homeo or homo means the same. Stasis is to stand or to stay. The same. To stand or stay the same. Now, it's misleading. The term is misleading because nothing in your body stays exactly the same. There's always some fluctuation up and down. But we use this term homeostasis, which implies things stay the same. In fact, they're not quite the same. There's always some fluctuation, but they're not. It's not a wild fluctuation up and down. So you translate the term, it translates as to stay the same. It would be a little more accurate to say certain features are held within narrow limits. If anybody asks you for the definition for homeostasis, you say it's the idea that things stay the same. But you'll understand it's be more accurate to say they're being held within narrow limits. So for instance, if you were measuring the temperature of your house, let's say that it's a winter day, it's 35 degrees outside, you've got the thermostat set for 68 degrees, you can make a graph. $70 degrees, 65 degrees, and so on. You make a graph, 60 degrees, 70 degrees Fahrenheit, and the thermostat is set for 68 degrees. Now let's say that when you start making the graph, the temperature in the room is about 66 degrees. So you start the graph at 66 degrees. The thermostat is a little device that is it's got a thermometer in it. So the thermometer knows what the temperature is. And you've set the thermostat, we could call it the set point, we've set it for 68 degrees. And the thermostat sees, oh, it's only 66 degrees, so it sends a message to a furnace. The furnace turns on, heats air, or let's say it heats water. It works, the example works a little better with a hot water heating system. So instead of a furnace, it's got a boiler. The boiler comes on, it heats up water. When the water hits a certain temperature, a pump comes on and pumps the hot water through radiators located in the different rooms in the house. Depending on what kind of system it is, I believe that the water temperature is about 90 degrees, but I'm not certain. So you have hot water running through the radiators. Heat radiates away from the radiators and warms up the room. So the air temperature starts to rise. Now, as the air temperature rises above 68 degrees, I guess you can see that. As the air temperature rises above 68 degrees, the thermostat sees, oh, it's warmer than 68 degrees, I'll turn the boiler off. So the thermostat sends a message to the boiler, turns the boiler off. Even though the boiler is turned off, there's still hot water in the radiator. So heat continues to radiate from the hot water into the room. So for some period of time, the room continues to heat up. So maybe it goes up to 69 degrees. And then the heat has left the hot water. It's colder than 69 degrees or whatever you have. It's colder than that outside. I think I said it was 45 degrees outside. So heat is now leaving the building, and the air temperature starts to cool off. And it cools off and cools off until it goes down below 68 degrees. As soon as it goes below 68 degrees, the thermostat detects that the temperature has fallen below 68 degrees. It sends a message to the boiler comes on and heats up the water, and then starts to pump the water through the house. Now, all of that takes some time to heat the water up and then start pumping it around the house. So the temperature might fall a little bit further before it starts to warm up again. And then as you rise past 68 degrees, the boiler turns off, but there's still hot water in the radiators. So the water continues to heat the room until the heat has left the hot water, and now it gets cooler, and then we turn the boiler gets turned back on, but it takes a few minutes to heat the water and send the hot water to the different rooms. So during that period of time, the temperature kept going down, but eventually it starts to come back up again. So the set point of the thermostat is 68 degrees, which is shown as this straight dotted dashed line. But if you actually measure the temperature of the air in the room, it's fluctuating up and down. And the way I told the story, and the way I'm just sort of describing what's going on, at the highest point, the temperature was maybe 69 to 70 degrees. Let's just make it 69 degrees. And maybe fell to 66 degrees. So when I say that, in this case, the air temperature, it's not staying constant at 68 degrees. It's fluctuating between roughly 66 and 69 degrees. It's being held within narrow limits. With respect to these narrow limits, what are the limits? Well, the lower limit is 66 degrees, and the upper limit is 69 degrees. And that's really the way things work in your body. They're not absolutely constant, absolutely the same all the time. There is some fluctuation, but it's not a wild up and down fluctuation. It's held within narrow limits. So, if I asked you to pause the video in a moment and make a list of things in the body, in your body, that are held within very, very narrow limits, what would you come up with? Why don't you try that? Pause the video and see how long a list you can come up with of things that are held within very narrow limits. And you should, I think the most obvious is body temperature. Held roughly 98.6 degrees, depending on where you're taking the temperature, what part of the body you're measuring. But the number that's generally given is 98.6 degrees. Blood pressure stays more or less the same. And this is all assuming that things work normally. People sometimes do develop high blood pressure, but when things are normal, the blood pressure is held within narrow limits. The blood gases. And what are the blood gases? O2, which is oxygen, CO2, which is carbon dioxide, blood glucose, which is a sugar that's in your blood, and this glucose sugar is used for energy, blood calcium levels, blood volume. A lot of the things are things that we find in the blood. A lot of these things that are held within narrow limits. The total fluid volume in your body. And the list goes on and on. These features that are held within narrow limits. Now these features can be called homeostatic constants. So if somebody says, give me a list of, give me 3 examples of homeostatic constants, you could say body temperature, blood glucose, and blood volume. And again, we're calling them constants, but they're not really constant. There's always some fluctuation. Now, I'm always tempted to wait a minute for you to finish copying, but obviously, I keep saying it's obvious. If it's so obvious, why do I feel like I have to keep repeating it? I don't know. You tell me. Now, there's a phrase which I like to spend a little bit of time on that relates to homeostasis. The constancy of the internal environment. Now, it's more or less a way to summarize homeostasis, the constancy of the internal environment. And it's got the same problem as the word homeostasis, which is constancy. Again, it's not constant. Now, one of the things I like about this phrase is that it contains an oxymoron. What is an oxymoron? It's when you have 2 words together that have opposite meanings. What is the oxymoron in that phrase? Well, before I tell you that, let me tell you my little oxymoron joke. So in class, I would usually give some examples of oxymorons, like jumbo shrimp, military intelligence. That always offends the people that have been in the service, and I apologize, but I've got to go for the cheap laugh. Jumbo shrimp, military intelligence. And once when I was giving some examples of oxymorons, a guy in the back of the room called out, happily married. Now that was 25 years ago, and it's important you understand, I didn't say that. Some guy in the back of the room said, happily married. I have been repeating it for the last 25 years, but I wasn't the one that said it. So what is the oxymoron in this phrase? Internal environment. How do those words have opposite meanings? Internal is inside, and the word environment means surroundings. It just occurred to me to say, and I don't know how significant it is, but on the YouTube videos, below the video, there's the letter CC, which means closed caption. So if it would be helpful to anyone to be able to read what I'm saying as I'm saying it, click on the closed caption button. Inside, the environment is the surroundings. And where are your surroundings? They are outside. So it's an oxymoron. Now, what could it be referring to? What could the term internal environment be referring to? And it refers to the tissue fluid. So the tissue fluid, it's internal because it's inside of your body, and its surroundings because it surrounds something. So what does the tissue fluid surround? You should know this from the discussion of the lymphatic system. The tissue fluid surrounds the cells. If you were a cell, your environment, picture yourself as being a cell. Picture yourself as being a cell in somebody's stomach. You'd be surrounded by tissue fluid. So your surroundings would be the tissue fluid. Both you and the tissue fluid would be inside the body, internal. So the internal environment is the tissue fluid. And we must have a constant, stable tissue fluid, because the cells, which are the building blocks of your living things, they need a certain amount of oxygen. They can't survive if there's too much carbon dioxide building up. They need a proper temperature. I left out acid-base balance, blood pH, acid-base balance. You might want to add that to your list of homeostatic constants. The pH balance must be very finely controlled for your cells to stay alive. So in order for your cells to stay alive, this tissue fluid which surrounds them has to have exactly the right amount of different things. So we want the tissue fluid to be more or less constant in that way, and that's just another way, it's a phrase, in constancy of the internal environment, which is summarizing the same idea as homeostasis. All right, so the specific example that I give of how the body maintains homeostasis is to talk about the pancreas. And the regulation of blood glucose. So the pancreas is an organ that's tucked in below and behind your stomach. You might want to look up image of pancreas in the body or something like that. Get a clear idea of what pancreas, what its location is. And the pancreas helps to regulate the blood glucose level. Now, whenever I talk about regulation, I like to point out that when we see something is being regulated, in this case the blood glucose level, it implies that there would be a problem with too much or too little of whatever it is that you're regulating. Because if there were no problem with too much or too little, you wouldn't need to regulate it. Most of us have a limited amount of money. We don't have, most of us don't have billions of dollars. And so we have to keep track of how fast we're spending the money. We have to regulate the speed at which we spend money. But if we had billions of dollars, or in my case, even millions of dollars, would be enough to last the rest of my life. And I wouldn't have to worry about how fast I'm spending the money. But if it's a problem, if you're spending the money too fast, it has to be regulated. So when we see something is being regulated, it implies there'd be a problem with too much or too little of whatever it is that's being regulated. Now, what's the problem with too much glucose in the blood? There's a few problems. One is that the glucose molecules start to stick to or attach to certain other molecules on the surfaces of different cells in your body. And when the glucose, it's like, you can think of it like wax sticking to something. And when the glucose molecules stick to these other molecules, it interferes with the functioning of these other molecules. So that's one problem with having a blood glucose level that's too high. Another problem with having a blood glucose level that's too high is normal urine has no glucose or very, very little glucose in it. Because, well, I don't want to get too sidetracked, so I'm just going to say normal urine doesn't have any glucose in it. If your blood glucose level is too high most of the time, then you end up with glucose leaving the body with the urine. And that's very wasteful because you spend most of your time making sure that you have enough glucose in your blood. And if the glucose was to leave the body with the urine, it would be horribly wasteful. I could make the argument that where you ever happen to be right now watching this video, why are you spending the time to watch the video? To some degree, it's to make sure that you have enough glucose in your blood. You're watching the video so that you can get an education, so that you can get a decent job, so you can earn money to buy groceries, so you can eat food. And part of the reason why you need to eat food is you need to take in glucose, the carbohydrate. Most of the carbohydrate in the food you're eating ends up being broken down into glucose in your body. So you're spending much of your time efforting to have enough food to eat, and part of the reason why you're doing that is to have enough glucose in your blood. If the glucose was leaving the body with the urine, it would be horribly wasteful, and things wouldn't work out very well. So that's the problem with too much glucose in your blood. What's the problem with too little glucose in your blood? The main problem is that your cells use glucose as a fuel for energy. Your cells need glucose for energy, particularly the cells in your brain. And then if the blood glucose level fell too low, the cells would be threatened for a lack of glucose. They'd be threatened with not being able to have enough energy. So the point isn't so much to memorize what I just said about high and low blood glucose levels. The point is to understand when we see something is being regulated, it suggests there's a problem with too much or too little, or too fast or too slow. And I'm just, going over that example with glucose. Now, I'm going to put a diagram on the board, and I've never put this diagram on this particular board. I'm used to putting the diagram on a bigger board. So you might think, well, why didn't I practice ahead of time? And right now I'm wondering the same thing myself. Why didn't I practice ahead of time? I don't know. It's probably got something to do with the incredible degree of laziness that I possess. But in any case, I didn't practice ahead of time, and I'm not going to pause the video and practice now. So hopefully I'm going to be able to squeeze this into this board. And the thing that you need to know is that there's going to be 1, 2, 3, 4 little blocks of information. And you have to copy 1, 2, 3, 4 little blocks of information. Then it's going to go down, and there's going to be 1, 2, 3, 4 blocks of information, and then it's going to go back up. So we end up with a loop. It's going to be a rectangular shape, but it's going to be a loop in the sense that it keeps going around and around and around. Now, when I do this in class, it's very important that people understand 1, 2, 3, 4 blocks of information. Since you will have a video showing the 4 blocks of information, if you get it wrong, the first thing, again, I'm always encouraging you to actually be taking notes on these videos. And if you mess this up, it's not a big problem. You just cross it out, rewind the video, and start it again. So the way this story begins is, let's imagine that you just ate lunch or whatever meal it happened to be, and it was a very high carbohydrate meal. Just to be ridiculous, let's say you had a bowl of spaghetti with some garlic toast on the side, and the spaghetti itself would have a lot of starch, which is a carbohydrate, and the bread of making the garlic toast would have a lot of starch, grains. Flour is made from wheat. Wheat is a grain. Both the spaghetti and the bread would probably have been made from wheat. Grains have a lot of starch, again, a carbohydrate. Potatoes, corn, these types of foods have a lot of starch, which again is a carbohydrate. Now, when I talked about the ribosomes, I said the ribosome is the place where proteins are made, and a protein was a necklace-like molecule. And I said there's going to be a few times during the semester when I talk about necklace-like molecules. And as soon as I tell you that a molecule is a necklace-like molecule, the next thing I tell you is, what are the beads that make the necklace? Starch is the second necklace-like molecule we're coming to. It's a very long molecule. It's made out of beads. In the case of starch, the beads are all glucose. So if you think of glucose like a white bead, we string together these white beads called glucose, and once we've strung them together to make a necklace, hundreds of glucose beads long, now that's called starch. So when you're eating pasta or bread or cereal, things like that, you're taking in a lot of starch, which is a long chain of glucose. And you need to deliver the glucose molecules, pardon me, you have to deliver the glucose molecules to your cells because, why? There's a reason, because the cells need the glucose for energy. Now, it's the way it kind of works is you have a digestive system, you chew the spaghetti, you're chewing the garlic bread, you swallow it, which essentially means you're pushing the food from your mouth into your throat, and the throat is the pharynx, P-H-A-R-Y-N-X, pharynx, that's your throat. Then it leads into a tube called the esophagus, which goes to your stomach, which goes to your small intestine, which goes to your large intestine, then out of the body. So when the food is going through the small intestine, that's where most of the digestion is happening. To digest is to break down. What I'm about to say is an oversimplification, but it'll help us understand what's going on. You can think of the wall of the small intestine has capillaries embedded within it. The lumen of the small intestine, do you remember what the word lumen means? So if this is part of the small intestine, buried within the wall of the small intestine, there'd be capillaries. And the nutrient molecules, this is the lumen, the hollow part of the organ. The nutrient molecules, N-U-T, for nutrient, have to get absorbed into the blood as the blood is running through the capillaries. And in order to get into the blood, the nutrient molecules have to cross the wall of the capillary, which has microscopically small pores. So anything larger than the pores in the wall of the capillary could not be absorbed into the blood. The starch molecules are too large, and as starch, they couldn't cross the wall of the capillary and get absorbed into the blood. So that's part of the function of the digestive system, is to chop this necklace up, chop it up into individual beads of glucose, which are small enough to get absorbed into the blood. So you're eating this meal that contains, what does it contain? It contains a lot of starch, and we're digesting the starch, breaking it down into glucose. The glucose is getting absorbed into the blood. So roughly 45 minutes to an hour after you've eaten this carbohydrate-rich meal, you have a high blood glucose, a high blood glucose level. Now, this is the first of 4 blocks of information. So don't write high blood glucose, because you won't be able to fit in the 4 blocks. High blood glucose level. Then there's going to be another block, another one, and another one. Now, when I say it's a high blood glucose, I don't mean it's abnormally high. It's just on the high side of the normal range. The pancreas, that's an N, pancreas detects the high glucose. So the pancreas is keeping track of the whole thing. It detects the high blood glucose. Now, when the pancreas sees that the blood glucose level is too high, it wants to send a message to the liver and tell the liver to store glucose. So the pancreas is below your stomach and your liver is up over here, and your pancreas needs to send a message to the liver and say store glucose. Now, among the 11 organ systems, could you tell me which 2 are most likely to be involved in carrying a message from the pancreas to the liver? And hopefully you could guess. It does require some critical thinking to figure it out, so it might not be that obvious. But the 2 systems would be either the nervous system or the endocrine system, which are the 2 systems that are usually involved with carrying messages around your body. So it could be the nervous system or the endocrine system. It's actually the endocrine system. And how does the endocrine system communicate? It communicates by secreting hormones, which go into the blood, and then the blood carries the hormone to a target. In this case, the target would be the liver, and the hormone sends a message to the target. So the pancreas starts to secrete insulin, which is a hormone. Now it's going to do something else, and we'll come back to that later on. The pancreas detects the high glucose. It starts to secrete insulin. The insulin tells the liver to store glucose. So picture the liver taking glucose out of the blood and storing it. As the liver takes glucose out of the blood, what's going to happen to the blood glucose level? Well, you should be able to figure that out. The blood glucose level is going to fall. So there's your 4 blocks of information, and I'm very happy to see it fit straight across the way I needed it to. you eat a carbohydrate-rich meal 45 minutes to an hour or so after you've eaten it. Much of the glucose is getting absorbed into the blood. You've got a high blood glucose level. The pancreas detects the high glucose. It starts to secrete insulin, which is a hormone that carries a message to the liver. And the insulin tells the liver to store glucose. And because the liver is storing glucose, the blood glucose level falls, and it falls until you have a low blood glucose level. Low blood glucose level. The pancreas detects the low glucose Well, as soon as the pancreas detects the low glucose, the first thing that it does is it stops secreting insulin. I hope that that would be obvious to you. The only thing that insulin can say to the liver is store glucose. So if the pancreas were to keep secreting insulin, the insulin would keep telling the liver to store glucose. The liver would continue to take glucose out of the blood, and the blood glucose level, which is already low, would continue to fall even lower. So the pancreas stops secreting the insulin, and the insulin stops telling the liver to take glucose out of the blood to store it. So we partially solved the problem of the glucose going into the liver for storage. However, even though the liver is no longer removing glucose from the blood, other cells in the body would be continuing to use glucose for energy. So the other cells in the body are removing glucose in the blood and using it for energy. So even though the liver stopped, when we stopped secreting the insulin, the liver stopped taking glucose out of the blood for the purpose of storage. But the blood glucose level would continue to fall as other cells or tissues in the body would continue to remove glucose from the blood for the purpose of using the glucose for energy. So this is a necessary step. We have to stop secreting the insulin, but it's not sufficient to prevent the blood glucose level from falling even further. Now, what the pancreas would like to do at this point is send an opposite message to the liver and tell the liver to release the glucose. Instead of taking it out of the blood and storing it, the pancreas would like to be able to tell the liver, release the glucose back into the blood so the glucose level, which is too low, starts to go back up. And in order to send that opposing message, the pancreas secretes a second hormone. So at this point, number 2, the pancreas starts to secrete. To secrete is to put out. The gland puts out the hormone. It starts to secrete a second hormone called glucagon. It's just another hormone. It's going to carry the different message. Now, some of you may know that there's a carbohydrate called glycogen. If you don't know it, don't be too concerned about it just now. But you may already know that there's another carbohydrate quite similar to starch. It's called glycogen. And in fact, it's going to be part of this story, but we won't come to it. Hopefully I'll remember to mention it in the next video. I'm just pointing out that there's this carbohydrate substance called glycogen because that is a different word than the word glucagon. So as you're learning this, make sure you keep it straight. Glucagon is a hormone, glycogen is a carbohydrate. The glucagon, and there's 1, 2, 3, 4 blocks of information on the lower part. The glucagon tells the liver to release glucose. And when the liver's releasing the glucose goes back into the blood. And since the glucose is going back into the blood glucose rises. And it can rise until it's a little bit too high. And then we're back where we started. So this is a loop that continues around and around. Now, it continues around and around throughout your whole life as long as you're doing something periodically, very regularly. So take a moment, pause the video if you need to. What would you have to be doing regularly in order to maintain this loop going around and around and around? Well, the answer is you have to be eating periodically and taking in more carbohydrate, more glucose, because if you weren't periodically taking in glucose, eventually you'd run out of glucose. That's called starvation at some point. And as you run out of glucose, this loop is going to come to a stop. Now, if you understand this as I've described it, and you may have to read through it several times before you can answer this next question. But if you understand it, you should be able to fill that blank in on your own. So pause the video. Even though it's paused, you can still look at the diagram. Read through the diagram several times and try to get to the point where you could fill that in. Don't cheat. Pause the video. Well, if you figured that the answer is stop secreting glucagon, then it indicates you probably understand the diagram as I've described it. So here we start secreting the insulin, here we stop, here we started secreting the glucagon, here we stop secreting the glucagon. Now take time with this diagram, get to the point where you understand it, but it takes time. It's not going to jump into your head in 2 seconds. Give yourself the time to learn the information. Take care. We'll see you before too long.